As you can see in my previous video, nerds93, I have run into a problem that I attribute to poor isolation between these two units. These are my 10 MHz oscillators. They are both connected to a buffer amplifier, this one and, well, this one and that one. That is to isolate from signals from the other oscillator. I will use this AirSpy HF Plus to look at how much signal is coming back from one into the other. So I stop this one from oscillating by removing the feedback, and then I can look in this connector like this. The signal level I see is minus 118.6 dBm, and I have calibrated the S meter before doing this. Now I'm looking the other way, so I have switched off this one and looking at how much comes from the other. And you can see the boxes are different. This one has some soldered copper on the sides, which this other one is missing. The level I see now is not very different, minus 119.8, so it's more or less the same. When I move the amplifier like this, the level is much lower, below minus 134. So the other box is sending its fields into this one that I moved. I have to believe that this box, which is less well screened, is surrounded by 10 MHz fields that are picked up by this other box. And the problem is not the signal coming through the coaxial cable going backwards through the amplifier. First I connect both sides of the copper laminate together with some thin copper foil like this, and I will do it on all sides. Both sides of the copper laminate are connected together everywhere on the box now. This is the forward frequency response, 9.5 decibel on 10 MHz, and it's fairly flat. I'm sweeping plus minus 2 MHz. This is the forward frequency response, 9.5 decibel on 10 MHz, and it's fairly flat. I'm sweeping plus minus 2 MHz. An inductor from input to output improved the isolation, but I don't like that, so I swapped the wires on the secondary winding on the transformer. So now I can use a trimmer capacitor instead. As it turns out, that's the one. I need also a couple of resistors in series with it. And that gives me this reverse response, minus 64 decibels. Now, this is critical. If I change the supply voltage, it will degrade. But I will keep it close to 16 and hope that aging is not going to be a big problem. At least it should be much better than before. The signal is very weak now. The S meter shows minus 141, but that's mainly noise. I have to make the bandwidth smaller to see mainly the signal. Something like that. Minus 144 dBm now. So it was 118 before, and this is something like 24 decibels improvement. Now this one is running and this one is stopped. So I am looking at the other input of a buffer amplifier with the AirSpy. The level here is significantly stronger. The S meter tells me minus 132. and it was minus 119 before. While I was measuring with the air spy and moving the cable, the BNC connector happened to touch here. Minus 16 volts and a very big electrolytic capacitor. Of course, this air spy doesn't work anymore, but the USB controller does. But the problem is, on the same USB hub was also my UADC4, and that doesn't work anymore. So now I don't have the UADC4 to verify the results of what I have done. I can use the SDR IP. It should be compatible, but there is more amplitude noise in the SDR IP, so there may be some difficulties to see. And I also don't know whether there is some phase noise in the PLLs of the SDR IP. The phase noise I see is the same as before. It's 87 at this point, and a little noisy, of course. This is how it compares with the previous measurement with the UADC4, before I made this improved isolation between the oscillators. And you see they are the same, differ by 1 dB only, and in both directions. And here is the amplitude noise. It's also the same as before, minus 100 at 0.1 Hz. As you can see, they are the same. So I realize I have made a mistake. These numbers, they represent the sideband noise of the Wenzel oscillator, suppressing the carrier as well as the noise doesn't change the carrier to noise ratio, because the interferometer cannot add any phase noise. I have now set 60 decibels of carrier suppression, and the phase noise I see has not changed much. Statistics is not so good. I have only collected 49 averages so far, but that will be enough now. The amplitude noise is very different, however. It has increased by about 20 decibels. The amplitude noise is very different, however. It has increased by about 20 decibels. I have set the carrier suppression to 80 decibels now, and I can see the phase noise of the interferometer. Here, minus 68 decibels at 0.1 Hz. As expected, the amplitude noise at 0.1 Hz is minus 60 decibels, 0.1 here. And this is with only 27 averages. The imaginary part is far below the real part, and still well above at the highest frequency I see here, which is 0.4 Hz. There is a significant correlation between AM and phase noise, so part of the phase noise comes from the same source as the amplitude noise, but there is also a lot of amplitude noise that has some other origin. When I compare the result with 60 decibels carrier suppression and 80 decibels, I can see the difference is not far from 20 decibels. And more close to that for the amplitude noise, which is much stronger and has better statistics. I have corrected for the carrier suppression, and here are the results. The phase noise, it looks like 6 decibels for a doubling of the frequency offset, while the amplitude noise looks like it is 1 over F, just 3 decibels for a doubling of the offset. So that is normal flicker noise. This is, I don't know, there shouldn't be any in a attenuator or connector, which are the sources of noise I think I have. The device under test is this box, but I have connected a straight wire from input to output, so actually there is no device under test. This is just the interferometer. But when testing amplifiers, I have these extra attenuators, this one on the output and the other one on the input, to be able to set the appropriate input level and then to set a gain that the interferometer can cope with. These are two of the attenuators in the interferometer, and some of the positions are painted red. And the same for this attenuator and switch, which is also incorporated in the interferometer. These red positions mark positions that are particularly noisy and should be avoided. I will now make some software changes and test these other attenuators to find if there are any noisy positions that they have. With 80 decibels of carrier suppression, things are very sensitive. If I, for example, just put my hand here, you can see how the level changes drastically. So everything has to be very calm, and one has to be careful when doing these kinds of things. Connectors, for example, I touch this one a little. Here I'm using 60 decibels of carrier suppression, and I get the average of the amplitude noise values from here to all the way here. It's from 2 Hz up to 34 Hz or so. And you can see the values, they come up here, and they will converge pretty fast, because the imaginary part is at least 6 decibels below the real part. So I wait for maybe 100 values. Then it will have converged to well within half a dB. I have added one more 6 dB amplifier, because higher power makes flicker noise more visible. So I have now plus 22 dBm in each leg of the interferometer. When looking for noise in attenuators in the interferometer, the input and output is this one and that one. And then the switch is inside this box. And in the other leg there are 2 attenuators, one that can be set in 0.1 dB steps and another in dB steps. I call them dual and single. I can set various combinations of these to achieve balance. When I set, for example, 2 decibels on the output or 2 decibels on the input, I get very near the same results, but when I set 2 decibels on the input, but change in the amplitude to have 1 decibel on the dual rather than 1 decibel on the single, I see an improved result. Means this is a little bit more noisy, but only 1 dB. And further down I see differences up to 1 dB, which is not significant, I think. This one is marked red on the attenuator, but now I find that this line and that line are very similar. So this isn't so bad as I thought. Maybe there was a contact problem long ago when I used this to make this study. Then I have used that attenuator and turned it across this position many times, and maybe the contact has improved because of that. Anyway, the table continues. These ones were both marked red, and the results don't differ significantly. But when I continue, I find a poor value, 103. And I repeat and find 104. But between those I had touched the attenuator. There is a bad contact, and I have marked this one red. And there is another one, the 20 dB, on the same attenuator. So this one is bad. It means this attenuator and this one. So I will avoid the 9 dB and the 20 dB position for this attenuator, the input one. But maybe with the time they will become okay also.